Projections estimate that by 2050, antimicrobial resistance or AMR can cause 1.91 million deaths directly and also contribute to 8.22 million deaths worldwide. The regions expected to experience the highest AMR mortality rate across all age groups include South Asia and Latin America and Caribbean. The most significant increase in AMR-related death is anticipated among the individuals aged 70 and older, who are projected to account for 65.9% of all AMR attributable deaths by 2050. Only in 2019, antimicrobial resistance were responsible for 29,000 direct deaths and associated with 3.57 million. Silver has been used for centuries as an effective antibacterial agent in various forms, such as metallic silver, silver salts, and colloidal silver. It seems that the ancient people were aware that solutions such as water and wine are preserved longer in silver containers. Therefore, the kings usually use the cups made from silver, and they use big silver containers to save the water in the prolonged wars. Nowadays, products based on silver nanoparticles are usually used in clinics, such as, for example, wound healing, disinfecting agents. It is generally known that the release of silver ion is directly connected to the antimicrobial action of Ag nanoparticles or silver nitrate or other silver-based antibacterial agents. In general, the antibacterial impact increases with increasing Ag plus or Ag ion concentration, and Ag plus has a superior antibacterial effect than Ag0. The first mechanism of bacteria to limit the toxicity of Ag nanoparticles is the formation of biofilms. The EPS or extracellular polymeric substance constitute 90% of the biofilms and are primarily composed of polysaccharides, proteins, nucleic acids, and a small fraction of lipids. And we know that the EPS matrix acts as a primary line of defense, physically obstructing the penetration of Ag nanoparticles into the deeper layers of the biofilm. The EPS is a complex mixture of biomolecules with nitrogen and sulfur containing functional groups, providing ample size for Ag nanoparticle complexations. Studies have demonstrated that when silver nanoparticles undergo sulfation and are transformed into silver sulfide, a compound with extremely low solubility will be produced, which the release of silver ions are significantly suppressed. This transformation greatly diminishes their antibacterial effects, reducing the inhibition of bacterial growth. Moreover, interactions can lead to the formation of EPS corona on the Ag nanoparticle surface, effectively masking the nanoparticle and hindering its interaction with bacterial cells. Surprisingly, reducing activity of EPS was shown to be increased under sunlight irradiation. In this matter, reducing functional groups in EPS found can act as an electron donor, and light can accelerate the transfer of electrons from EPS to silver ions. In addition, EPS molecules can be activated by light to generate potent reducing agents. Equally, is able to produce compounds such as pyocyanin to induce the reduction of Ag plus to Ag0, which is considered to be an important survival strategy for bacterial resistance to heavy metal ion toxicity. The other compound that might affect is nitrate reductase, an enzyme within the nitrogen cycle accountable for transforming nitrate to nitrite. As it reduces Ag+, nitrate reductase gains electrons from NADH and oxidizes it to NAD+. Also, you may saw some articles which are using bacteria to produce Ag nanoparticles. Obviously, the interaction of these two compounds is totally different. The antibiotics enter to the cytoplasm using transmembrane diffusion and porin-mediated diffusion. The porin channel has size limitation up to 10 angstrom, which allows to transport the low molecular weight molecule. In mammalian cells, the nanoparticle enter via endocytosis pathway, which is not available in the bacteria. Therefore, the nanoparticles must interact with the cell wall and membrane of the bacteria. Bacterial cell can develop resistance to metallic nanoparticles by decreasing the expression of porins, thereby limiting the entry of ions or overexpressing efflux pump system to transport ions. As we talked previously, bacteria can reduce the toxicity of Ag nanoparticles or Ag plus by preventing them from coming into contact with the cell or by inducing the reduction of Ag plus to Ag0. Moreover, Stabrilla et al. Found that E. coli K12 bacterial cells could develop heritable resistance to silver nanoparticles by mutating the CUSS gene, a copper silver ion sensor that regulates the expression of CUS-CBA efflux transporter to mitigate the toxic effects of these metals. Okay, let's talk about remodeling the cell envelope. By altering the fatty acid composition, bacteria can effectively modulate the physical properties of their cell membrane, increasing the proportion of saturated or longer chain fatty acids or incorporating cyclopropane fatty acids can enhance membrane rigidity. This makes the bacterial cell envelope more resistant to mechanical penetration of carbon nanotubes, thereby reducing the likelihood of cell damage and death. Additionally, isomerization of cis to trans unsaturated fatty acids in the membrane and modification of the lipid composition of the membrane can alter the fluidity of the membrane, resulting in resistance to heavy metals. We know that the bacteria mostly represent a negative charge. However, it was found that bacteria reduce the negative charge on the membrane surface by modifying the phospholipids in their own cell membrane as a result, reducing the interaction with the antimicrobial peptide and reducing its effect. Gram-positive bacteria can protect themselves from contact with positively charged nanoparticles by incorporating D-alanine into the cell wall and reducing their total negative charge. As we discussed earlier, the antibacterial activity of silver nanoparticle is highly controlled by their dissolution rate. Generally, silver nanoparticle aggregation exhibits decreased antibacterial performance due to reduced release of silver ion from silver nanoparticle in aggregation states. In contrast, an increase in the amount of dissolved silver nanoparticle provides more silver ion to kill bacteria, therefore enhancing the bacteria killing ability. Also, this aggregation of silver nanoparticles can reduce the contact between silver nanoparticle and bacteria. In a study by Panacek and colleagues, silver nanoparticle with the size of 28 nanometer was synthesized. We know that in general that the antibacterial activity of the nanoparticles could be more effective if their size typically be around 50 nanometers. So the size of this article is so perfect. 20 successive bacterial cultivation steps were conducted for each tested bacterial strain in media containing sub-inhibitory concentration of silver, measuring the MICs of the silver nanoparticles after each step. E. coli CCM3954 was the first bacterium to develop significant resistance to the silver nanoparticles. By the 6 cultivation steps, its MIC was notably higher than that of the reference strain, and in the 8th step, the MIC had increased to 54 mg per liter. Interestingly, when ionic silver was introduced to the culture medium in a separate set of experiments, there was no observed increase in MICs. This suggests the bacteria did not develop resistance to ionic silver under tested conditions. Additionally, the MICs for ionic silver were the same for both the silver nanoparticle resistant bacteria and their non-resistant parent strains, indicating that the resistant mechanism effective against silver nanoparticles does not apply to the ionic silver. Therefore, the induced bacterial resistance appears to be specific to silver nanoparticles. So, what happened? Large aggregates of silver nanoparticles with sizes ranging from several hundred nanometers to micrometers were observed after culturing with age-resistant E. coli CCM3954. One question: can surfactant mitigate this problem? Addition of polyethylene glycol, polyacrylic acid, twin AT, and protein gelatin were not affecting the resistance process. Experiments using the commercialized flagellin has shown that this protein has the dominant effect on aggregation. In 2021, Estabila and colleagues also tested some bacteria without the genes associated with flagella expression. The result was interesting. Their results revealed that the absence of flagellin led to the Ag nanoparticle aggregation. This suggests that other bacterial components, such as pili, outer membrane proteins, ribosomal proteins, and enzymes, may also contribute to the aggregation of silver nanoparticle. Faghizadeh and colleagues also observed that extracellular polymeric substances secreted by E. coli can induce the aggregation of silver nanoparticles. They found that EPS interacts with Ag nanoparticles to form Ag nanoparticles. EPS